नमस्ते दोस्तों, today we have part third of lecture number 18. Before that, we have discussed two results related to polynomial ring, in which result 1 states that if R is a commutative ring with unity, then the polynomial ring Rx will also be a commutative ring with unity. In result number 2, we have learned that if R is an integral domain, then the polynomial ring Rx will also be an integral domain. So, today we are going to discuss result 3, in which we are going to find that if R is a field, then whether polynomial ring Rx will also be a field, will also be a field. This is the result we are going to learn, because we have seen that if commutative ring with unity is the parent ring, then the polynomial ring will also be a commutative ring with unity. If the parent ring is integral domain, then the polynomial ring will also be an integral domain. So the result 3 discusses that if parent ring is a field, then whether polynomial ring will also be a field or not. So we are going to find the answer of it while proving with one counter example. So we are going to first see the proof, then we are going to write the result. So I am just first explaining the proof. So if a structure is a field, when we say that this algebraic structure is a field, then we say that this structure is commutative ring with unity, and for every non-zero element belonging to ring R, there exists an element A superscript -1 such that when we operate A with A superscript -1, we will get the unity element. Basically, for a structure to be a field, we have learned that it must be a commutative ring with unity, and every non-zero element belonging to set R has multiplicative inverse. Means when we operate that element with its multiplicative inverse, we get the unity element. So if in order to prove that the polynomial ring Rx is field or not, we have to show that if there exists at least one, if we are able to show at least one example that this particular element has no multiplicative inverse, then we can say that the polynomial ring will not going to be a field. So we are going to consider one counter example which will show us that if the parent ring is a field, then the polynomial ring will never be a field. So the example which I am considering, you can see, consider fx equal to x. This is the element which is going to be present in every polynomial ring, which is fx equal to x, and this is the non-zero element belonging to set Rx. Now, we are going to let that this particular element belonging to polynomial ring Rx has multiplicative inverse. So, we are going to consider let Gx, which I define like that, b0 plus b1x plus b2x square plus dot dot. I am going to rub this be a multiplicative inverse of fx. If I say that gx is the multiplicative inverse of fx such that then if I operate fx with gx, we get the unity element which is ex in the polynomial ring Rx. I am defining here where ex is the unity element of Rx. Basically, I have stated in previous lectures also that the parent ring and the polynomial ring will have the same unity element. So Ex is basically 1. The notation which we use to represent the unity element in R is 1. So the constant term here will be 1, and if you are going to express in the polynomial form, then you can expand like that 0 dot x plus 0 dot x square, like that, dot dot dot. I think this I can remove, so I am erasing it. Now if you see fx is x and gx is a polynomial b0 plus b1x plus b2x square plus dot dot dot, and now if we multiply x with each element of the terms of polynomial gx, we get b0x plus b1x square plus b2x cube plus dot dot dot. And if you see that there here in this term on the left hand side, there is no constant term is mentioned. Every term is multiplied with the variable, you can say, symbol x. So we can here put 0. 0 is not, after adding this 0, it doesn't change the meaning of the whole term. Here we have just expressed, since the constant term is not present, so we are able to define the constant term as the 0 element of the ring. So here is the term which we get after multiplying the variable x with the each term of the polynomial gx. And on the right hand side, we have 1 plus 0 dot x plus 0 dot x square plus dot dot. So if you compare right hand side and left hand side, you get on comparing we get, if we compare the constant term, here the constant term is the 0 element of the ring, and here the constant term is unity. So will this 0 element of the ring and the unity element of the ring will going to be equal? This is not going to be possible in any scenario. This will never will going to occur. So we can say that which is not possible, which is not possible at all. This will not going to be occur. As a result, we can say that thus gx, or I can say fx equal to x has no multiplicative inverse in Rx. So this is what we have to show, and we have shown it clearly that the polynomial ring will not going to be a field in any case. So if the parent ring is a field, then the polynomial ring will never be a field. Will never going to be a field. Why? Because we have shown one counter example, one element which is present in every polynomial ring, which is fx equal to x. And if you see this polynomial, the multiplicative inverse of this will not going to be present in any polynomial ring, because if you are going to multiply with and assume that there is a polynomial which is the multiplicative inverse of fx, then you will going to get the constant 0 element of the element equal to the unity element of the ring. But this is not going to be equal in any case. As a result, we have shown that this polynomial has no multiplicative inverse. And if we are able to show at least one element whose multiplicative inverse is not existing, we are going to define it that this will not going to be a field, because for a field every non-zero element has a multiplicative inverse, and this condition is not being fulfilled by any polynomial ring. As a result, if I have to write the statement of this result number 3, I can say if R is a field, if R is a field, then polynomial ring Rx, if R is a field, then polynomial ring Rx never be a field, will never be a field, will never be a field. It will not going to be a field. But we have learned in previous lectures that field implies integral domain. If you have not learned this theorem, I will recommend you to go to the description box, follow the link and see this lecture. Because here I have explained that every field is an integral domain. And in result number 2, we have seen that if the parent ring is an integral domain, then the polynomial ring will also be an integral domain. As a result, if R is a field, then R will automatically be a integral domain. As a result, the polynomial ring will never be a field, but it can be an integral domain. So I can state here also that if R is a field, then polynomial Rx I can rewrite in a different way so that it will be easy for you to understand that if R is a field, then polynomial ring Rx is an integral domain, but not a field, Here we can say that if parent ring is a field, then polynomial ring is an integral domain, but not a field. So I hope this result number 3 is clear to you. I will going to discuss some examples related to it so that you have a proper understanding of the result number 3. So now we are going to see some of the examples in which we are going to apply the result number 3. Here I have written some polynomial rings and we have to find whether these polynomial rings are going to be a field. So if you know result number 3, you can directly state that any polynomial ring, if you define on any field, it will not going to be a field again. That is, if you see that complex number, real number, rational number, ZP, Q root 2 and Qi, all these are field. And if you are going to define a polynomial ring on these field, then that polynomial ring will not going to be a field. No. The polynomial ring defined over complex number is not a field. The polynomial ring defined over real number is not a field. The polynomial ring defined over rational number is not a field. The polynomial ring defined over ZP is not a field. Although these all parent rings are field, but the polynomial ring is will not going to be a field, because in every polynomial ring which I have stated here, there is an element whose multiplicative inverse will not going to exist. For a particular case, we can take fx equal to x. This is the element whose multiplicative inverse is not going to be present in all these respective polynomials. As a result, they are not going to be a field. Similar case is going to apply in here also, where q root 2 defined as a polynomial ring over a rational number q root 2 is not going to be a field. Similarly, the polynomial ring defined over Q O iota is not a field. But all these polynomial rings are integral domain. are integral domain. These all are integral domain because field implies integral domain, and if a parent ring is integral domain, then the polynomial ring is will also going to be an integral domain. As a result, the polynomial ring defined over rational number, complex number, real number, over ZP, over Q root 2, over Q iota are integral domain. So I hope today you have successfully learnt about result number 3, and with this example you are pretty much clear that if the polynomial ring is given and you have to identify whether these polynomial rings are going to be a field or not, you can directly state that these are not going to be never be a field, because there are elements whose multiplicative inverse will not going to be present in that polynomial ring. So I hope this lecture is clear. If there is any doubt or any portion of the lecture is not clear to you, you can directly ask in the and mention in the comment section. Thank you.